In today's video, we're going to look at rational functions and see exactly what rational functions are. We're going to look at exactly how we would graph those. So there are things called asymptotes and holes that we're going to look at, and then that way you will be able to recognize a graph of a rational function and also graph whatever function you are given. So what exactly is a rational function? A rational function is just a function where you have a polynomial divided by a polynomial. So for example, you could have something that looked like x squared plus 1 over 3x cubed plus x minus 2. That would be a rational function. You have a polynomial divided by a polynomial. Something that wouldn't be a rational function would be something like this. Your denominator is still a polynomial, but your numerator is the square root of x. The square root of x is not a polynomial. It is not of the form a times x to the power of a whole number that is greater than 0. So we have to make sure whenever we do this that everything in these rational functions, both numerator and denominator, satisfy that definition of a polynomial. So go back to our last video and look exactly at what polynomials are. Okay. The next thing we want to look at is the domain of rational functions. Okay. When we have a rational function, it's a polynomial divided by a polynomial. The rational function will obviously not be defined whenever that denominator is 0. It doesn't matter what the numerator is. As long as that denominator doesn't equal 0, it means that it is defined. So the domain of a rational function is all real numbers, but we've got to take out any value x that makes a denominator 0. Okay? We'll do a couple examples of this. So let's say we had f of x is equal to 2x plus 1 over x squared minus 9. Okay. What's our domain of this? Well, it's all real numbers, but we've got to take out any value x for which our denominator, x squared minus 9, equals 0. Okay. So if we set our denominator equal to 0 and solve, you may have to do some simple factoring. I would never give you any problem when you're doing any like factoring of cubics or quartics or anything, but you may have to factor a quadratic here if it's not already factored, and you set it equal to 0 and see what values of x give you that 0 denominator. So this particular rational function is defined everywhere, so the domain here is all real numbers, not including -3 and 3. You could also write that in set notation if you wanted to, but this is just the easiest way to write it. Another quick example is something like this. And the question is, what is the domain of this function? Well, again, it's all real numbers except for where that denominator is 0. Unless I deal with complex numbers here, this is actually defined for all real values x. Okay, I have to go into the complex numbers in order to find an x where this is 0. Because if you went ahead and solved this, you would be taking the square root of -1, which is obviously a complex number, not a real number. So in this case, our domain is just all real numbers. One more example that I want to look at is if you get a rational function of this form. So it was already factored, but you find that you have the same term in the numerator and denominator. Do not cancel those out. Your domain is still all real numbers except for where that denominator is 0. We'll look at what happens for this particular function where you have that like term that is in both the numerator and denominator, and what happens with simplifying it, etc., etc. That's where asymptotes come into play. But in terms of your actual domain, do not cancel it out. Your domain is still all real numbers, in this case not including -1 and -3. The next thing I want to look at is the x and y intercepts of a rational function. A quick example that I'm going to look at for these x and y intercepts is a very simple rational function, just 1 over x. Okay, again, both your numerator and denominator are both polynomials. You've got the constant polynomial in the numerator, and then you have x in the denominator. This actually has no x or y intercepts. If you go back to the graphs of our basic functions, you can see that the graph of 1 over x looks like this. It never actually crosses the x or the y axes. So this has no x or y intercepts. Why is that? How do we find x and y intercepts? Well, x intercepts are found when y is 0, and y intercepts are found where x is 0. So if I say y is equal to 1 over x, if I try to find the y-intercept, we'll start there. For the y-intercept, you set x equal to 0. Well, if I try and do that in this case, I would end up with 1 divided by 0, which you can't do. That's undefined. So we know that there is no y-intercept because I can't divide by 0 in this case. How about an x-intercept? For an x-intercept, we set y equal to 0. So if I did that here, I would have 0 is equal to 1 divided by x. 1 divided by anything is never 0. Okay? There is no way that I can get 0 by taking 1 divided by any number. So there is no x-intercept for this function. So that explains why we have a graph that looks something like this with no x or y-intercept, is because when we set x equal to 0, we end up with something undefined, and when we set y equal to 0, there's no way that we can get 1 divided by x is equal to 0. So there is no x or y-intercept. Just as a heads up, when you do this, you will see this more and more as we go along. If you are trying to find the x-intercept, so you set y equal to 0, setting y equal to 0 for a rational function is equivalent to just setting that numerator equal to 0. Okay, let me come back to another function. Let's say this function that we have here. Okay, if I set this function equal to 0 to try to find those x-intercepts, so if I said 2x plus 1 over x squared plus 1 equals 0, because I was trying to find my x-intercepts here, so I set y equal to 0. Where does this function equal 0? Well, it only ever equals 0 when the numerator equals 0, because that would then be 0 divided by whatever it might be equals 0. That's the only way that I can get 0. So that's the same thing as saying 2x plus 1 equals 0, which would mean that x would equal -1/2. So that would be the x-intercept for that particular function. So just as a side note, whenever you get one of these problems and they ask you for the x and y-intercepts, the y-intercept, you just set x equal to 0 in the problem, solve for y. When you're asked to find the x-intercept, so you set y equal to 0, for a rational function, that's just equivalent to setting the numerator equal to 0, and it makes it a lot easier to solve. I'll do a quick example here for this so that we can see this in action. So the first thing that I'm going to do is look at x plus 5 over x squared minus 9, and I'm going to try and find the x and y intercepts of this particular function. So for the y-intercepts, I set x equal to 0. So if I do that, I end up with my y-intercept would be 0 plus 5, which is just 5, over 0 minus 9, which is negative 9. So my y-intercept would be at 0, negative 5 over 9. Okay. For my x-intercept, I set y equal to 0, which means I just set my numerator equal to 0. So that would be x plus 5 equals 0, which would imply x is equal to negative 5. So my x-intercept would be negative 5, 0. Okay. One more example of this would be f of x is equal to 3x squared minus 15 over x. Okay. For my y-intercept, I set x equal to 0. Well, if I do that in this case, I would end up with negative 15 divided by 0. Again, I cannot divide it by 0. So therefore there is no y-intercept because I end up with something that's undefined. For my x-intercept, I'm going to set y equal to 0, and that's the same thing as setting my numerator equal to 0, which will give me 3x squared is equal to 15, which means that x squared equals 5, which means that x is equal to plus or minus the square root of 5. That means I have two x-intercepts here. I have no y-intercept, but I actually cross the x-axis twice. So my x-intercepts are going to be the square root of 5, 0, negative the square root of 5, 0. Okay. Now, very much like what we had with that graph of 1 over x. Okay. You'll notice here that I have things called asymptotes. Asymptotes are just lines that the graph approaches but never touches. Okay. When we look at this vertical asymptote here, the vertical asymptote for f of x is equal to 1 over x is actually just the y-axis. It's x is equal to 0. That is the vertical asymptote of this particular graph. The question is, how do we find that vertical asymptote for other rational functions? Do they exist for every rational function? How do we find those? Okay, so we're going to look at vertical asymptotes first, and then we will look at horizontal asymptotes, and then actually oblique asymptotes after that. So how do we find these vertical asymptotes for a particular rational function? I'm going to do this via an example. And then you can extend this to other examples as well. So if we're looking at the vertical asymptote for this particular function, I have actually factored this already just because that's how we're going to use the function in this particular case. But if you have a rational function, first thing you want to do is factor the numerator and the denominator. So in this case, we've already got it factored, but if you hadn't factored that denominator, make sure that you do that. So you factor the numerator, factor the denominator. You'll see that we actually have x plus 5 in both the numerator and denominator. We saw from our domains that this function is not defined at x is equal to 4 and x is equal to negative 5. So at x is equal to 4 and at x is equal to negative 5, we know that this function is not defined. Okay? But we actually see this particular term in both the numerator and denominator. So if we were trying to simplify this function, we would cancel out the x plus 5s. But our function is still not defined at x is equal to negative 5. So we have to be aware of that when we cancel those out in terms of our domain for the function. We'll actually get to that when we look at wholes of the function. But what you want to do is factor this and then cancel out any terms that show up on both the numerator and the denominator. So in this case, we could cancel out the x plus 5s. So in simplified form, we would get 1 over x minus 4 for this function. Okay. Like I said, we will talk about what happens for those terms that we cancelled out later on. But right now we want to look at the simplified form of the function. Anywhere, any x value that gives you a 0 for the denominator in simplified form gives you a vertical asymptote. Okay, so like I said, we will deal with that x value of x is equal to negative 5 later on. But at this other x value that still hangs around once we've done all this simplifying, it's that x value that makes your denominator 0 when you are in simplified form. Okay, that is your vertical asymptote. So at x is equal to 4, you have this vertical asymptote. So you'll find that the graph will approach that vertical asymptote but never touch it. Okay. We'll do another example here. So now if we had, for this example, f of x is equal to 3x plus 1, x minus 4, over x plus 1, x minus 7. Okay. This time, okay, again, I've got it factored for both the numerator and the denominator. There will be times when you will be given these rational functions where you will actually have to factor the numerator and denominator. Again, I won't give you anything that's cubic or quartic or anything like that. It will be at most a quadratic that I would ask you to factor, but there may be times that you will have to do that, so just be aware of that. But I've already got them factored here just so that we can see exactly what we need to do to find those vertical asymptotes. So we can see that, again, the domain of this function is all real numbers, but we will take out anywhere where that denominator is 0. So in this case, our domain is all real numbers except for when x is negative 1 or 7. Okay. But when we're looking at where the asymptote is, where that vertical asymptote is, we simplify this. So we see that we have x plus 1 in both the numerator and denominator. So we can simplify this and cancel those out. So in simplified form, this would be my rational function. Now I look at where the denominator equals 0 and any x value where the denominator equals 0 in simplified form means that I have a vertical asymptote there. You may end up with multiple vertical asymptotes. That's fine. Just be aware that it is where you've got the simplified form of f of x and then you set your denominator equal to 0. Do not do it before you've put it in simplified form and cancelled out any like terms on the top and the bottom. Okay. So in this case, we set our denominator equal to 0, and that tells me that I have a vertical asymptote at x is equal to 7. So make sure that you simplify first, then set your denominator equal to 0, and that will tell you where your vertical asymptotes are. And like I said, you may end up with more than one. Okay. If we had another term that was in our denominator here, so we had a third term, that would mean that I could have another vertical asymptote even after cancelling out. Okay, so just be aware of that. The next thing that I want to look at is horizontal asymptotes. So we've already looked at the vertical asymptotes, but now we want to look at the horizontal asymptotes. again, if we look back at our graph of f of x is equal to 1 over x squared, we saw that we had that vertical asymptote, which was the y-axis at x is equal to 0. We also had that horizontal asymptote that happened when y equaled 0. It was the x-axis. Okay. The thing with the horizontal asymptote, which is unlike the vertical asymptote, you can sometimes see that the graph may actually touch the horizontal asymptote at some point here or there. But the main thing with a horizontal asymptote is we want to see what happens for the end behavior of the graph. So what happens as x goes towards infinity, what happens as x goes towards negative infinity. If we look at our graph, I'll make a quick sketch of 1 over x. Okay. We saw that it looks something like this. So we can see that as x goes towards infinity, because we have that horizontal asymptote, you see that the graph, as x approaches infinity, y is getting closer and closer and closer to 0. Same thing happens as x goes towards negative infinity. Y gets closer and closer and closer to 0. So that is basically showing us the end behavior of the graph. You may find with some of these problems that you end up with a graph that will look something like this, where it may touch that horizontal asymptote at some point and then carry on. Okay, that's fine. It's just going to touch it across it at certain points. But the main point of our horizontal asymptote is to show us that end behavior. What happens as x goes towards infinity and x goes to negative infinity. So if, let's say, y is equal to b is a horizontal asymptote. Okay. That tells me that as x goes towards both positive and negative infinity, f of x, or the y value, will go towards b. So in this case, for y is equal to 1 over x for that particular graph, we saw that as x goes towards both positive and negative infinity, that f of x goes towards 0. Okay, for both cases. So that is the point of a horizontal asymptote, is to show that end behavior. There are 3 cases that we have to deal with horizontal asymptotes that you'll have to remember. And it all depends on the degrees of the polynomials in your numerator and denominator. Okay. So let's say that you have f of x is equal to some polynomial p of x divided by another polynomial q of x. Okay. The first case that you'll come across is that the degree of p of x is less than the degree of q of x. Okay. So an example could be, let's say, f of x is equal to x over x cubed plus 1. Okay, that would be a particular example where the degree of p of x is 1 and the degree of q of x is 3. Okay. That tells me, if that is the case, that y equals 0 is the horizontal asymptote. Okay. That's our first case. The next case that we have is where the degree of p of x is greater than the degree of q of x. Okay, so an example of this would be f of x is equal to, we'll flip this around, x cubed plus 1 over x. In that case, there is no horizontal asymptote. You'll actually find, and we'll look at this later on, is that you get something called an oblique asymptote in this case. but there is no horizontal asymptote whenever the degree of P of x is greater than the degree of Q of x. The last thing that we have to be worried about is when they are actually of equal degree. So if the degree of P of x equals the degree of Q of x, what happens in that case? Well, remember what our polynomials look like, okay? So let's say that P of x is equal to an x to the n plus an minus 1, x to the n minus 1, and you go all the way down until you get to the constant at the end. And Q of x would look something similar. I'll use b's in this case. Okay, where each one of these a's and b's is just a constant, okay? And remember, in this case, we're saying that they have equal degree, so they will both be of power x to the n, would be in the leading term. If that is the case, so you've got equal degree for both P of x and Q of x, then y is just the fraction made up of the leading coefficients. So it's the ratio of the leading coefficients. So an, which is the leading coefficient in px, okay, so it's that term that is the constant in your leading term. It's that coefficient of x to the n, where n is the highest power. An is your numerator, and bn, the one that's the leading coefficient for Q of x, that is your denominator. So y is equal to an over bn is the horizontal asymptote. Okay. We'll do a quick example of some of these. So the first one that we'll do is f of x is equal to x cubed over x to the 4 minus 5. Okay. In this case, the degree of P of x, the degree of our numerator, is less than the degree of our denominator, so that tells me that y equals 0 is the horizontal asymptote. Okay, so as x goes towards infinity and x goes towards negative infinity, you'll find that this function goes towards 0. A quick example to show you that you may end up with random points where the graph of this function actually touches the horizontal asymptote. Okay, it won't stay on the horizontal asymptote, but it may touch it at random points, which is unlike the vertical asymptotes. You'll actually see here that 0, 0, the origin, actually satisfies this particular equation. Okay, it satisfies this function. 0, 0 is a point on the graph of this function. Doesn't happen all the time, but in this case it does, that you end up with a particular point that satisfies this function that is also on that horizontal asymptote. Okay, just kind of be aware of that. You won't find that a function will hang out on a horizontal asymptote. As x gets bigger, both positive and negative, you'll find that it will go closer and closer and closer to that asymptote, but won't actually touch it. It may just touch it at random points like we see here with the origin. The next example I'm going to do is f of x is equal to 2x squared plus 3x plus 1 over 4x squared plus 5x minus 3. Okay. In this case, they have equal degree. They both have degree 2. So our horizontal asymptote in this case would be y is equal to 2 over 4, the ratio of the leading coefficients, which is just y is equal to 1/2 is our horizontal asymptote. And the final example that I'll do here is f of x is equal to 3x cubed plus 2x plus 1 over 4x minus 5. Okay. In this case, we have that the degree of the denominator is less than the degree of the numerator. So p of x has greater degree than q of x. So that tells me that there is no horizontal asymptote for this function. In the next video, we're going to look at those oblique asymptotes where you get a function that is exactly like this example here, where you have that the degree of the numerator is greater than the degree of the denominator. And we'll look at what those asymptotes look like and how we actually find those, because we know that there is no horizontal asymptote, but you will find those oblique asymptotes. And then finally, we're going to use that in order to actually graph each one of these functions. So that will be in our next video.